We're going to begin our calculus study by talking about the idea of a limit. The idea of the limit in calculus was born when mathematicians decided to ask, what if we could divide by zero? We know how to do all of these things mathematically, except when we run into trouble. And the biggest offender in mathematics is dividing by zero. So they wanted to know, can we get a better understanding of what's happening to a function where it's undefined, specifically where it's undefined because of division by zero. And this is the basis of a limit. And the limit is foundational to the study of calculus. If we ignore what's happening at an input value that has no corresponding output value because the function's undefined there, can we gain any understanding by looking at what's happening to the output very, very near those input values that give us division by zero? Remember, on the real number line, we talked about the idea of the denseness of the real number line. And at any given value on the real number line, here we'll call it the x value of c, very, very near that value, to the right or to the left, we can get as near to that value as we want to get and still put it inside of our function. We could say we're putting a value a little bit smaller than c into the function, and we're going to get a corresponding y value. We could also say we're putting a value a little bit bigger than c into our function. We'll still get a well-defined value. The only thing that gives us trouble is if we are at c, not near c. So the limit has everything to do with the idea of being near. On the real number line, how near, how close can we get to c but still not be at c? Well, because of the denseness of the real number line, we can get very, 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 very close. We can get infinitely close. And infinitely close for us means as close as we need to get. So when we talk about the idea of looking at input values very near a value that gives us mathematical trouble, that's what we're talking about when we deal with the limit. So let's look at a function. So let's look at this function. This is the function f of x equals x squared minus x minus 2 over the quantity x minus 2. This is a rational function. Rational functions are polynomials over polynomials. So this is a rational function. And we know that we could, with a denominator, we could have the possibility of having division by zero. And for us analytically, with the algebra that we know we're going to have trouble when x equals 2. The output of this function when x equals 2 is going to be undefined, and we can clearly see that here on a table of values. We can also see that evidenced here by the hole in the graph of this function at an input value of x equal 2. So we know we have trouble at 2. We know that what happens to f of x at x equals 2 is that it's undefined. Mathematically, we're very comfortable with that. So the limit says we're not going to worry about what's happening at. Let's discover or explore what might be happening near that input value that's giving us trouble. Let's approach input values along the x-axis, the real number line for our independent variable. Let's approach them from the left. I'm going to use a little superscript negative sign. So from the left, I'm going to go up here, and the outputs of my function, here are the y values. The outputs of my function are approaching this value along the real number line. They are approaching 3. Now, they're not at 3, they're just near 3. That's 3.0. Let's see what's happening to the output values as we approach input values from the right. Those are values a little bit bigger than 2. So we go up here to our function, we trace along the function, and we see that along the y-axis, the output values are approaching 3 again. They're approaching 3 from values above 3. Again, we can see this evidenced on the graph. When we approach 2 from the left, values smaller than 2. The outputs approach 3 from below, values smaller than 3. If we look at what's happening to the right of 2 along the x-axis, we're approaching values of 2 that are bigger than 2. And along the y-axis, we are approaching values of 3 from above, values that are bigger. Now again, at x equal 2, we are undefined. And here is the idea of the limit. The limit shows the y values, the output values, get near, not at, but near 3. And that's the idea of the limit. There's some notation that goes along with this. And so what's happening near x equal 2 on this function is we say the limit, and that's LIM, shorthand for limit. Right underneath that we would say as x approaches 2 of our function, and our function is x squared minus x minus 2 all over x minus 2 equals 3. So the limit says, what do the outputs of the function do as the inputs get very near this value? That is the limit. The limit gives the output of the function. Remember, limits are outputs. The result of a limit is a y value. That's very important. So now that we've explored the idea of the limit, let's see where it comes from. Does it matter if the function is well defined at the value where we have mathematical trouble? Here's a piecewise defined function. We talked about piecewise defined functions before. And this is the original function we were looking at on the last slide. Same thing we were looking at on the last slide. We can see that on the graph. We can see that over here on the table. But it just so happens that at x equal 2, now instead of being undefined and having a hole, we have an output value. And that output value is right here. It's a y value of 1. So this tells me that f of 2 exists and it equals 1. So this is a piecewise defined function. Now it's not a continuous function, but it is defined everywhere. We can see as we approach values of 2 from the left and values of 2 from the right, the same thing is happening as was before. Our outputs are approaching 3 from below and 3 from above. So the limit still exists and the limit is still 3. So now we have a well-defined function at x equal 2. We have an output. Does that change the limit? No. We don't care in a limit. We never care about what is happening at. We only care about what is happening near. That's all we care about. The limit doesn't matter about what's happening at. We can have a well-defined, we can have a smooth continuous function, but we can still talk about the idea of the limit. So here is a definition of a limit. To say that the limit as x approaches c of some function equals capital L means that when x gets near, when input values get near, but different from c, because we're approaching c in the limit, then the output values, the y values, the f of x values, get near L. So here, the output values at 2 are 1, but as we get near 2 from the right and from the left, the output values get near 3. So we don't say 2.999 is the limit or 3.0001 is the limit. The outputs are getting near 3. We do have more specific limits that help us discover what's happening near an input value. And those are called one-sided limits. One-sided limits. Because we did, if you'll notice before, we did discover what was happening when we approached values from the left of 2, and then we discovered what was happening when we approached input values to the right of 2. So we have one-sided limits, and they have everything to do with left and right. So the left-sided, sometimes called the left-handed or left hand, both of those are equally correct names, limit, has a little bit different notation. And that's why I've been using that superscript. Here we would say the limit as x approaches 2 with a superscript negative means from the left. That's how we would say that. The limit as x approaches 2 from the left of our function. So we're approaching 2 from values less than 2. That's from the left along the real number line for the x-axis. The outputs are approaching 3. So the left-hand limit here is 3. Again, I care not what's happening at. The function may be well defined at. I'm inside of the limit, and the limit says I'm just near. So there's the left-handed limit, and there is the notation that you need to know for this one-sided limit. As you can guess, there is a right-handed limit or a right-sided limit. The right-sided or right-handed limit is written as the limit as x approaches 2 with a superscript plus sign, and that is read from the right. So the limit as x approaches 2 from the right of our function is. When we approach input values from the right, the output values are approaching 3. So this right-sided limit is 3. For the overall limit to exist, both one-sided limits must exist and must be equal. So here's another example. Here is another rational function. This time, this function, we can tell algebraically, is going to have trouble when x equals 1. It's going to be undefined there. We can see that evidenced on the graph. We can see that evidenced on the table. So we would say, let's explore our one-sided limits. If we're approaching 1 from the left, we can see that our outputs are approaching 3 from below. Same thing is happening here on the table. Table of values and what's happening on the graph are identical. So we would say the left-handed limit, the limit as x approaches 1 from the left of our function equals 3. And we would look at the right-handed limit or the right-sided limit, and we would say the limit as x approaches 1 from the right, the superscript plus sign, of our function equals 3. So the overall limit, the first limit that we looked at, what's happening on both sides of 1, there is no superscript plus or minus there. That means I'm looking at what's happening from both approaches near 1. Are my outputs approaching the same output value? Still, the limit as x approaches 1 of my function does equal 3. Why does it equal 3? Because both one-sided limits equal 3. If that wasn't the case, then the overall limit would not equal 3. So it's important that the outputs from the right and from the left on our input values, it's important that the outputs both approach the same value.